Hi everyone, this is Sumit. Welcome back to my channel. Today's topic is P, NP, NPC, and NP hard problems. This topic is one of the most important topic and also one of the most confusing topic, but I will try my best to make it easier for you. Let's dive into it. So this is the outline of the video. First, we will understand the time complexity. Then we will look at the definition of P and NP with examples. To understand NP, we will need Turing machines, so we will understand that from higher level. We will look at NPC and NP hard problems with examples, and finally, we will see why is all this so important. In computer science, the time complexity is the computational complexity that describes the amount of time it takes to run an algorithm. Time complexity is determined by a fixed set of operations such as loops, constant operations. Since an algorithm's running time may vary among different inputs of the same size, computers' processing speeds, hardware configurations, computer scientists came up with these three following metrics to measure complexities. The first one is big O, and it specifies the worst amount of time any algorithm can take for any given input. This is the most commonly used metric because we want to see how the algorithm performs for the worst input. The second one is big theta, which specifies the average amount of time. And the last one is big omega, and it represents the best case. So while we use these metrics, we assume that n is very large. For smaller inputs, these metrics are relatively insignificant. So let's understand these time complexities with the help of an example. We have to search values in this array, and you can see that this is unsorted. In order to search elements in this array, we would have to check the target value and compare it with every element in the array starting from the left. We can also start from the right, but I'm choosing to start from the left. So if we have to find 10, time complexity would be constant in that case. And you can see that it is the best case. So the best case time complexity is constant. Similarly, if we have to find 25, which is in the middle of the array, we would have to go halfway, which is n by 2. And after dropping the constant half, the time complexity will become theta n. While analyzing time complexities, we usually drop the constants. Lastly, if we have to find 50, which is in the end of the array, then the time complexity is big O of n, because we will have to check all the elements till the end. This is clearly the worst case. Let's look at the order of time complexities to see why do we care about time complexities so much. So you can see this table of time complexities. On the left hand side, the first column represents the value of n, and the rest of the columns represents the function or time complexities. So for n is equal to 10, which is the first value, we have log-based time algorithm such as binary search right here. It would take at most these many operations to find an element in a sorted array. In the case of linear search, we will have this number right here. So we will have to make 10 comparisons for array of size 10. And let's say if we have a sorting algorithm and we have to sort an array of size 10, these are the number of operations that would be required. And you can see how it is growing when we reach factorial time complexities. Just to give you a rough idea, let's say that each operation would take 1 second. And we have to find factorial of n is equal to 100, which is the second value. To find factorial of n is equal to 100, it will take these many seconds on the computer. For the sake of comparison, the number of atoms in the universe is approximately 10 raised to power 80. And you can see that this number is way too larger than that. Although the computer performs millions of operations per second, it would have no trouble calculating the factorial of n is equal to 100. But you know, when n becomes really large, like in millions or billions, you can imagine what trouble we are getting into. Calculations could take maybe years or light years to compute. So you can understand the real problem now. There are many examples of algorithms that run in exponential time, like subset sum, finding all binary representation of n length. And these algorithms do not have polynomial time solution. Somehow we want to solve these problems in polynomial time. If not solve it, then at least prove that no polynomial time algorithm can exist for such problems. Let's look at the definition of polynomial time algorithm. An algorithm is solvable in polynomial time if for some k which is greater than 0, its running time on input size of n is O n raised to power k. For example, n, n square, n cube, etc. So these are polynomial time complexities. Let's look at definition of NP time algorithm. So NP stands for Non-Deterministic Polynomial Time Algorithm. NP algorithm can be solved in polynomial time by non-deterministic Turing machine. Let's understand what is non-deterministic first, and then we will understand what is Turing machine from high level. So let's look at this example to understand what do we mean by non-deterministic. So this is an algorithm for searching an element in the array. The problem is to find a value in the array, and the array is unsorted. So from the linear search perspective, it takes linear time in the worst case to search an element in the unsorted array. Let's look at this algorithm which does it in constant time. So the function find takes a, which is the array, and the value which we need to search in the array. This function magic takes the array and returns an index. We check if the value at the index matches with the target value. If it does, we return found, and if it doesn't, we return not found. If we analyze the time complexity, the if statements will take constant time. But what about this magic function? Remember, magic is not like a random function. It takes in the array and it gives the correct index. But we do not know how it is implemented, but it makes the overall time complexity constant. This is called non-deterministic, the state of not knowing. I know this is weird, but it will start coming together, so be with me. So the purpose of this was to explain you what non-deterministic means. Now let's understand what is Turing machine. A Turing machine is a mathematical model of computation that defines an abstract machine. A Turing machine is capable of simulating any algorithm's logic and giving result in finite time. All in all, whatever can be done by the computer, the Turing machine can also do that. And whatever cannot be done by the computer, the Turing machine cannot do that. So this definition is the definition of deterministic Turing machine. There is another type of Turing machine which is non-deterministic in nature. And the definition says that whatever the computer cannot do in polynomial time, with the help of some magic, the non-deterministic Turing machine can do it in polynomial time. Please remember, all this is theoretical. Turing machine is also a theoretical model which helps us to prove which problems are NP and which are not. So it's similar to saying that non-deterministic Turing machine can solve traveling salesman problem in polynomial time. Not possible at this point in time, but maybe in the future. For instance, it is possible that previously sorting was NP, but now it's in polynomial time. We hope to solve all NP problems someday in the future. But yes, it comes with pros and cons. So let's go back to a definition of NP problems. So these problems can be solved in polynomial time by non-deterministic Turing machine. And that's why we went through all those examples of non-deterministic, and also we understood what is a Turing machine. The full understanding of Turing machine is out of the scope of this video, and it is studied under the subject of automata. At this point, it's time to introduce what is an NP complete problem with the help of an example. This is a Sudoku, and you have to solve it. The rules are that all the rows, columns, each of the sub-block right here should not repeat the numbers between 1 to 9. This is a classic backtracking problem, and it takes exponential time to solve it. Here n is 9, so we can still solve it. Imagine if n becomes very, very large, then this problem becomes intractable. This is an NP problem. Now, let me change the way how this problem is asked. What if I gave you a solution to this problem? Can you verify it in polynomial time? You can take your time to think while you pause this video. So I think it can be done in polynomial time. You just have to check that if any number is repeating in any row, column, or in any block, and return true or false accordingly. And I think this can be done in O of n squared time, which is polynomial. This becomes a decision problem of the original NP problem, where we assume that some oracle or magician has given us the solution and we have to verify it. And this version of the problem is called NP-complete problem. Examples of NP-complete problems are SAT, satisfiability problems, circuit SAT, subset sum, clique problems, vertex cover, traveling salesman, etc. etc. For a minute, just believe me that any of these problems can be converted to any other instance of the problem with the help of reduction. I will not be covering reduction in this video. What it means is, if any one of the problem is solved in polynomial time, then all the NP-complete problems can be solved in polynomial time. Now this might seem a little interesting, but it has its own pros and cons. Think about the RSA encryption algorithm. This is an NP-complete problem. To decrypt RSA 768, it would take 2000 years. And to decrypt RSA 1024, it would take 2 million years. But if you are given the decryption key, you can certainly decrypt it in polynomial time. This brings us to the definition of NP-complete problems. A decision problem of NP problem is NP-complete if it is in NP, it is verified in polynomial time, it is reducible to any other NP problem in polynomial time. So with the last statement, we try to prove that it is at least as hard as any of the existing NP problems. This reduction is proving NP hard. To prove that the problem is NP complete, you would have to prove all these things. Now you must be wondering, why is this so important? Let me give you two scenarios for that. So you get a job and you're asked to develop an algorithm, and somehow someone proves that the algorithm you developed is NP complete. So in that case, you will not be able to implement that algorithm. That is why we should know what these concepts are. Similarly, if you are designing encryption algorithm, you would want it to be an NP complete problem so that no one decrypts it. So finally, this brings us to the end of the video. Please subscribe, like, share, and comment on this video. See you in the next video. Bye!